This is my NASA mission. A week ago, G and I were called upon NASA, the National Aeronautics and Space Administration. NASA focuses on space exploration and aeronautic research. NASA has been trying to create a bit better spaceship to go into space. However, they've been having some critical engineering problems when they re-enter the atmosphere. It gets really hot when you try and come down into the atmosphere and you're exposed to a lot of space debris. Our objective is to create heat-resistant tiles for NASA, and it will be able to protect the passengers inside from melting away and protect from space debris hitting the spaceship. So the space tiles must be able to withstand impact, so that gotta mean it's hard. It's gotta be able to be heat resistant and take the heat from re-entry, so that means it has to have a high melting point and a low specific heat. And because our budget is $15 million, it has to be affordable. As we got this assignment, we were told to look out for the 4 main properties, physical properties that could help us with our material. Hardness, how a material could take impact; tensile strength, how easily it can break; elasticity, how much it can stretch; and melting point, the temperature which a solid turns to a liquid. Hardness and melting point were our 2 main properties. However, we also just noticed that we needed specific heat, but I'll go on to talk about that later. So we were given 4 main categories to choose the material: metal, polymer, wood fibers, and ceramics. We found that metals had a high boiling point and were very hard. Polymers were very malleable and had a high tensile strength. Wood fibers were soft and were not heat resistant, but that's because they catch on fire. And ceramics were hard and have a high boiling point. And from these, we found that metals and ceramics were our 2 main categories because they fit all of our criteria. There was another very big element that we had to include: the specific heat. The specific heat is how much energy it takes to make an object increase its temperature. A high specific heat means it's very easy to change the temperature, and a low specific heat means it's very hard to change the temperature. And we want a material that has a low specific heat. So we started with metals. We found that platinum and steel, although they have low specific heats, they weren't hard enough to take impact from space debris. And the aluminum and tungsten alloy were too soft and melted too easily. And so they wouldn't be able to take the heat from re-entry. So we went on to our second category: ceramics. Ceramics. So they all had low specific heat, but we found that quartz was not strong enough to take impact. And then between silicon and alumina, we chose silicon carbide because it has a lower specific heat. So silicon carbide has a hardness of 2,894. It has a tensile strength of 124, elasticity of 370, and its melting point is 2,700 degrees Celsius with a specific heat of 670 joules per kilogram. 20 metric tons of silicon carbide can be purchased for about $1,000. That's pretty cheap. But what makes silicon carbide the perfect match for NASA? It's the way the silicon atoms and the carbon atoms fit together. Silicon carbide is made of an infinite chain of atoms. They form in a network covalent bond which connects all the atoms together. That is what makes it hard. It is that the atoms don't have a certain place to break because they're all interconnected, and that is what makes the silicon carbide very strong. It is usually in a hexagonal structure. However, that is not always the case. Okay. The atomic structure is a covalent polar bond. This means that carbon is more electronegative than silicon. The covalent polar bond makes it so it's very difficult to split the 2 atoms. This is why it has a high melting point and a low specific heat. This formation allows for the low specific heat and for the high boiling point, as well as it's very hard. The network covalent bonds and the covalent polar bonds allow for the material to be able to withstand the impact from space debris, as well as resist the heat coming from the re-entry into the atmosphere. This is why silicon carbide is the perfect choice for the material used for the space tiles.